Hello and welcome back. We'll go on with a few more examples, but before that we'll look at the definitions of Cp and Cv, which are the specific heats at constant pressure and constant volume. So we know the definition of these. So for example, Cp is the amount of heat which is transferred for a unit degree rise in temperature for a unit mass of the substance at constant pressure. And similarly, Cv is the amount of heat transferred for a unit degree rise in temperature for a unit mass at constant volume. So if we were to write the formulae for Cp and Cv, we would write Cp is the amount of heat transferred for a unit degree rise in temperature for unit mass. So we would divide by mass, so this is delta T. So similarly, we would write Cv as the heat transferred per unit temperature for a unit mass. So we would have something like this. Of course, this is assuming a small amount of heat is transferred. If it's general amount of heat transferred, we would just write Q instead of having this del over here. That's also fine. So we can look at whether we can find out the value of Cp and Cv or find out relations between Cp and Cv and other parameters. So let us look at Cv first, for example. So if I have a box, a rigid container, so the walls are fixed. I have some amount of some gas, for example, I have mass m, and I transfer in some amount of heat Q. There is no shaft work, there is no electrical and magnetic work, there is no displacement work because the walls are rigid. So in this case, what we would see is that the work interaction for the system is essentially 0. So I transfer in some heat, the temperature of this substance is going to increase, or similarly I could transfer out heat and the temperature might decrease, but the work interaction is 0. And I can write first law for this system. So first law in the differential form would be this. In the integrated form would be of course this, and W is 0 because there is no deformation of this substance and no other forms of work are possible. So what I see is that the change in internal energy, change in energy is Q. Now if I have this system which is rigid anyway and it is stationary, so it is not moving anywhere, then in our general form we write that energy is summation of internal energy and potential energy and kinetic energy. If this box is stationary and not moving anywhere, so this is 0, this is also 0. So we are left with delta E is equal to delta U, which gives me delta U is Q, or Q represents of course the change in or the heat transferred in going from state 1 to state 2. I can also write it like this. Now what I can also do is write this delta U as m into small u, because the total change in internal energy is sum of is mass into the change in the specific internal energy. So I can write it in this fashion. So what I see is if I now compare here, I have over here Q is equal to m into Cv into delta T. I have over here Q is equal to m into delta U, which means that delta U must be equal to Cv into delta T, or over here Cv is essentially delta U by delta T, which is equal to delta capital U by m delta T. So we see that this is the expression which we get for the specific heat at constant volume. If I was to do a similar exercise over here we are looking at a constant volume process. So we are looking at a rigid box. For Cp, we are looking at specific heat at constant pressure. So we will need to look at a constant pressure process. So, we can look at, for example, a piston cylinder arrangement. It is not insulated. I have some heat transferred. I have a piston which is frictionless and will move when the pressure here reaches some value, and the pressure here is on both sides is balanced. In this case, it would be, for example, atmospheric pressure. If I had this system vertical and had some mass for the piston, it would be something else, but it's all right. This is a constant pressure process. I am transferring some heat Q. In this case, the piston is also moving, so there is some work which is also done, which is W, and it's a constant pressure process. So, if I was to apply the first law for this process, again the first law is given as del Q minus del W, or I can also write it as in the integrated form. Any of them is okay. So, in the differential form, this would be du by dt. This, of course, all of this is at constant volume. We already know that. I have not specified that. Usually, we would write over here saying that V equal to constant, but it's understood that this is at constant volume and this is at constant pressure. So, V is equal to constant. Over here, V is equal to constant. Capital V is also equal to constant. So, because we are looking at a system, so mass is constant. So, we have this kind of an expression. Again, by the same logic as here, this system is fixed. The system itself is not moving. There is no change in potential energy, there is no change in kinetic energy. So, I can write in this case this delta E is equal to delta capital U, or I can also write it as m into small delta U is this. What we see over here is that it is a constant pressure process. Let us say the pressure is some P, and in this constant pressure process, let us say the volume changes by some dV. So, let me take the differential form itself. So, I have here m du is equal to del Q minus del W, and this del W is essentially P dV. Because that is essentially the work done by the displacement of this piston. So, what I can see over here is that I have an expression of this kind, and del Q from here is m Cp dt. So, this is m sorry, I have made this as small v. So, I should also have mass here. So, capital V is essentially m into small v. M is a constant. So, I need to put the m also over here. I can cancel out the mass. So, essentially I get, I will cancel the mass and I will rearrange it. Cp dt is equal to du. I will take this to the other side as P dV. This is essentially what I have. Now, over here pressure is a constant. This is a constant pressure process we are looking at. So, I can also write this as du plus P dV plus V dP. Pressure is constant, dP is anyway 0. So, I am just adding 0. This entire term is 0. So, I am adding 0. This is what I can write, or I can write it as du plus d of PV. PdV plus VdP is d of PV. So, I have d of U plus d of PV, which I can write as d of U plus PV. And U plus PV is essentially what we call as enthalpy. So, this is essentially dH, which is the change in enthalpy. So, what I have here is that Cp dt is equal to dH, which tells me that Cp is at constant pressure. And if I was to write capital H, then I would write in this form. So, because we know that this is true, the extensive property is mass times the specific property. So, I can also write it in this fashion. So, what we see is from a definition of Cp, this is our definition of Cp. Cp is 1 by m del q by q by delta t, or 1 by m del q by dt is what we would also write. And so, this gives us this is our definition, but from the definition of enthalpy we also see that this is true. Cp is dH by dt as at P equal to constant. Similarly, over here we have del q is equal to mCv dt, or q is mCv delta t. That is our definition of Cv, and from there we see that Cv is also equal to du by dt at V equal to constant, that is equal to 1 by m d capital U by dt when V is equal to constant. So, we have expressions for Cp and Cv in this fashion, and we can calculate either the heat transferred in this case, which is connected to this, or we can calculate heat transferred in this case in terms of changes in internal energy and so on. So, that is something which is useful to keep in mind.